In this video, we're going to look at the entropy associated with phase changes and the entropy associated with heating. So first, turning our attention to phase changes. We know that phase changes occur at a given transition temperature, right? So we've got to have a transition temperature, right? So we're going to call that T sub TRS for the transition temperature, right? So just like with, if you're vaporizing water, that occurs at 100 degrees C at a constant pressure, right? So we're specifically going to be talking about the transition temperature at a constant pressure. So at 1 atm, let's say, right? So at standard pressure at 100 degrees C that if you boil, you put water up at that temperature, it's going to vaporize, right? Now, since we are at a constant pressure, right, we can make a statement about the heating, about the heat transfer and its relationship to enthalpy. So at constant pressure, at constant P, we know that Q sub P is equal to the enthalpy change, right? We know that the total heat transfer is going to be equal to the total change in enthalpy at a constant pressure. So what we can do here is define a entropy for the phase transition using this transition temperature and the enthalpy of that transition, right? So we can define an entropy of the transition by putting the enthalpy of that transition over the transition temperature. Right? So for any phase transition, you don't have to integrate in order to solve the entropy, right? So when we've been looking at these very general reversible processes, you always have to integrate from the initial to final temperature. But we know that phase transitions happen at a particular temperature, so we actually don't have to integrate. We just have to get the enthalpy associated with that phase transition, put that over the temperature associated with that phase transition, and we get the entropy of that phase transition. Now, this is in general, but usually we're looking at the standard enthalpy. So I'll go ahead and put that little circle in the superscript there, right? So we're usually looking at standard enthalpies, and so we're usually getting standard entropies of transition, right? So let's think about what the sign of entropy is going to be for different scenarios and what that can tell us about the entropy on a molecular level, right? So let's think about some exothermic transitions, right? Some transitions that release heat. So if the transition is exothermic, right? Let's say we have an exothermic transition. So this could be something like, freezing or condensation. So I'll put, for example, freezing. Any transition where you're going to be releasing heat as that phase transition occurs, right? So what that means for us for enthalpy, right? That means that delta H for the transition is going to be less than 0, right? And as far as the entropy, right? So let me keep that arrow going this way, right? So the transition is exothermic. That means that delta H is going to be less than 0. Since delta H is less than 0, that means that delta S is going to be less than 0, right? Our entropy associated with the transition is also going to be less than 0, right? So why is that, right? Look at this equation, right? You know that since this is going to be negative, the temperature in the denominator is going to be the absolute temperature, so we can't have a negative temperature. So we end up with a negative entropy. So what does this mean for our disorder, right? This means that we're increasing the order of the structure, right? So this is an increase in order, right? You end up with a more ordered structure, right? So you end up with a decrease in entropy. So this makes sense, right? Or you can think about it like from our statistical definition. You end up with fewer possible microstates for your molecular composition, right? So as you have an exothermic transition, you're increasing the order. So if we think about freezing, for example, you're going from a liquid to a solid, right? The molecules are going to be more tightly packed in a solid, so you're ending up with less possible microstates. That's going to be an increase in the order, right? So that's going to give you a decrease in the entropy, right? And let's look at the opposite, right? So let's look at an endothermic transition. So if the transition is endothermic, right? So this is something like vaporization, right? Vaporization or melting, what have you. Any of those exothermic phase transitions, then that means delta H for our transition is going to be greater than 0, which means that delta S for our transition is also going to be greater than 0. Right? So in this case, we're increasing disorder, right? So this is an increase in disorder, right? In this case, we're increasing the disorder, right? Because this is an endothermic process. It's releasing heat. You're going from a phase, an ordered phase, to a more disordered phase. So like, for example, with vaporization, you're going from a liquid to a gas where you can have many possible microstates, many more possible microstates in the gaseous phase than in the liquid phase, right? So, so we have these different general understandings of the entropy associated with a phase change. Now, the entropy of vaporization has a very interesting property. So what I'm going to do is list off the delta S, the standard entropy of vaporization. This is going to be in joules per Kelvin per mole for a couple of different species, right? So let's look at benzene. So for benzene, C6H6, its delta S of vaporization is about 87.2. For carbon tetrachloride, its delta S of vaporization is about 85.8. For C6H12, cyclohexane, its delta S vaporization is about 85.1. Right? Now, what do you notice about these? They're all roughly the same, right? Benzene's a little bit higher, but you end up with these numbers being very similar. And I could list off a bunch of different liquids that, when vaporized, give a delta S of vaporization of about 85 joules per Kelvin per mole. So this general observation is called Trouton's rule. So Trouton's rule is just the general observation that a wide range of liquids have the same delta S of vaporization. So a wide range of liquids have the same delta S of vaporization. Right? So a wide range of liquids have the same delta S of vaporization, and it's about 85, right? So about 85 joules per mole per Kelvin, right? So what's interesting, though, are the few liquids that deviate heavily from Trouton's rule. And I'll give you one example here. So one example of a stark deviation from Trouton's rule is water, right? H2O, which actually has an entropy of vaporization of about 109.1 joules per Kelvin per mole, right? So it's really interesting to think about why this one deviates further from Trouton's rule than most any other structure, right? And we can think about it on a molecular level, right? If entropy is a measure of, the amount of order your structure has, or how ordered a structure is, then what this deviation from Trouton's rule is really looking at is that there's a much larger change in order for a structure of water than there would be for benzene. So, when you look at benzene, right, benzene molecules get together, right? So this is one of my benzenes. Put another benzene here, right? Benzene molecules get together and they stack, right? They stack in this fashion. They do pi stacking, right? These are just rather weak van der Waals forces that pull these benzenes together, right? So when you vaporize it, it's not that much of a change when in the disorder of the structure, right? They're going to pull a little bit further apart. On average, they're going to be further apart. There'll be a little bit less of this pi stacking, but it's much less dramatic than with water, right? With water molecules, these guys come together and form hydrogen bonds, right? So you'll have, water interaction, doing something like this, right? Where we have a hydrogen bond, right? And these hydrogen bonds are much, much more stabilizing than these pi stacking interactions or any of the van der Waals interactions that will happen in any of these other molecules, right? These hydrogen bonds cause a much more ordered structure. So when you raise the temperature and cause this phase transition, you get a much more dramatic shift in the entropy because you're causing more of a change in the order of the structure. This structure of water is going to be much more ordered than any of these other structures that just rely on rather weak van der Waals interactions, right? So Trouton's rule, very, very general. You get a lot of liquids that follow Trouton's rule of having a delta S of vaporization of about 85. But it's really, really interesting to look at those points where we get these deviations from Trouton's rule. And water is one of the best examples of a deviation of Trouton's rule that you can look at on a molecular level and say, okay, this structure is much more ordered. So it makes sense that we have a much larger deviation here. Okay, so now let's look at the entropy associated with heating. So I've drawn a graph of the delta S, the change in entropy with respect to the ratio of temperatures, right? What you'll notice is that it has that same logarithmic dependence that we saw with the volume ratio as well. This same logarithmic curve with the ratio of temperatures. Now, why is that? Well, let's investigate it again and see what we can come up with, right? So we saw that for that isothermal process that we looked at, we saw that the entropy change would have a logarithmic dependence on the volume ratio. Well, in this case, if we're heating, then, it probably won't be an isothermal process if we're pumping heat into the system. Then if we're solving for the entropy change, right, we have our general equation for the entropy, dq rev over T, right? If we're going to integrate, right, we're going to have to integrate from some initial temperature Ti to some final temperature Tf of dq rev over T, right? Since this guy is not going to be isothermal, we can't just yank temperature out of the integral. So we're going to end up with a different expression. And we have to involve the change in temperature in this differential somehow. So what we want to do is use our definition of dq in terms of the heat capacity. So we can turn this guy into Cp dt over T, right? Just using our definition of the heat transfer, right? And then we can solve this integral by pulling out Cp and then just solving the integral of 1 over T, which will just be the natural log of Tf over Ti, right? So here again, by, just solving for the entropy change for this process, we're able to immediately see why we have this logarithmic dependence of the entropy change, right? It comes from the equation for solving the entropy change for an ideal gas during this heating process.